So point being, I've been on the generation side. I've worked at utilities like Portland General Electric. I've worked with CCAs. I've worked with communities. In 2016 with PECI, or was it 2019? 6, 9? We won a Visionary of the Year award through the Smart Electric Power Alliance for a community utility-owned microgrid. And I'd been working on things like microgrids and PPPs for a while and trying to solve real problems for real people. I remember being at a board meeting when I first came back to PECI the second time, and the board said, we want to do these microgrid things. And I said, you know, these seem like a solution in search of a problem to me. I'm not really in that business. That didn't go over super well, but you know, I said I really believe strongly that we have to provide value for communities, and there needs to be a real use case for this, not just something that is a science project that I'm interested in. So as I started digging deeper, if we want to move to the next, and it's not in here, so we'll just skip it, I think. Oh no, there it is. Okay. So in my slides, which I think are on the website that you can download, there's a link to the 7-minute presentation. It's like a TED Talk style, and it's talking about how buildings are the weird uncle of the climate crisis. So many of these technologies promise easy scale. Oh, EVs, oh, we can create this tech, and it's just going to solve a myriad of problems, and we'll be able to scale it because it'll be all these SKUs. But buildings don't let us harbor that illusion. They are too diverse. They are so heterogeneous. They, the controls are old. They have different types of manufacturers. Each of those has its own separate API. You try to regulate it, and people say, well, I'm using this standard. Well, I'm using this standard, and they don't talk to each other. And that's all fine and good, I guess. Eventually it'll be solved, right, by a market need. And I saw that a lot was happening in the residential sector in particular to try and understand this. I saw also that a lot of large organizations like Salesforce and Adobe were spending time trying to look at operational net zero in their buildings, and they had the capacity to do so. But as I started going out and talking to communities, I'm looking at Becky here because I remember talking to Marine Clean Energy. I started talking to cities that were trying to decarbonize, and what I saw was that people were starting to freak out in Washington, Oregon, and California, where I was talking to them, because standards were pushing them toward electrification, which they wanted. But utility prices were also pushing them toward using electricity at times of day where renewable generation was plentiful. But the two things weren't lining up. Like when their electric devices needed to use energy and when electricity was cheap, those were not matching. And in particular, in buildings that had large HVAC loads. And I think you mentioned earlier, even at the residential scale, what we were seeing is, for example, schools might have 150 rooftop units or heat pumps on their building. Throughout a district, you might have thousands of them. One all-electric high school in Tacoma, Washington has about 80 heat pump units, all electric, right? Raise your hand if you think you know what their morning startup peak was. 80 electric rooftop units.
It's all commercial, right? It's all commercial?
It's 2.4, yeah, 2.4 megawatts morning startup peak. Just insane, insane. And we look at California schools, which are far bigger, Antelope Valley, I was talking, and the thing is, what we were noticing, we did a project, I'm sorry, Ram's not here, he was our project manager, with EPRI and SCE before I started this company, working with 30 facility owners in publicly owned facilities that are not able to capitalize. These are old buildings, they have old equipment. It's very difficult for them to, you pass a bond for $2 billion worth of backlog, 5 years later, once the bond is passed, that backlog is now worth $5 billion and you only raised $900 million, right? So doing these big capital upgrades, pulling a bunch of SKUs off is not gonna work for them. They can replace a $6,000 heat pump by $6,000 heat pump. Your old gas RTU fails, you pay $6,000 for a new heat pump, one by one. That's how they do it. So what we saw was that these schools were spending literally millions of dollars. Schools that have massive solar arrays, massive batteries, places like Fontana Unified School District, where the logic on the battery too probably made sense for whoever owned it, maybe Tesla or someone, because they were bidding it into the market. But the minute that their huge solar array came online in the morning, they started charging the battery, adding 30% peak on top of what the HVAC was already doing. You might be talking about 150 HVAC units, 3.4 megawatt peak for some of these schools. The battery would then be totally full by 11 a.m. and start dumping 60 kW of solar at the lowest compensation rate in the day back onto the grid. And I remember saying to my CTO at the time, this is either the stupidest thing I've ever seen or so smart that I don't understand it. She's like, no, it's the stupidest. So it became obvious to me, if we go on to the next, that I wasn't going to solve, and this is just showing that this isn't just California. Dynamic rates and building performance standards are accelerating everywhere. In Washington State, that was another thing when I was interviewing these organizations. In Washington State, next year, 2026, building owners with over 50,000 square feet, average middle school in the United States is 73,000 square feet, are going to be fined $5,000 and $1 per square foot, so about $80,000 a year for not meeting an EUI of around 43, which is like every school I have ever encountered in my life. These are old buildings. They are old buildings. So I was sort of thinking, like, we don't realize this, but we are inadvertently, with these laws, which are well-intentioned, penalizing publicly funded, in general, mid-sized commercial that have very unsophisticated building operations and no means to really get there because their budgets are fixed when it comes to maintenance and operations. So let's go forward. Energy is the second largest expense for schools after labor. Many of the districts that are even wealthy and very sophisticated, one of our customers is Fremont Union High School District. You might recognize the communities of Sunnyvale, California, Cupertino. These are very wealthy neighborhoods. It's one of the nicest school districts I've ever seen in my life. They have smart EV charging. They have the coolest Daikin VRFs. They've got fancy new controls. They've got solar awnings everywhere, and they still spend upwards of $2 million a year on energy for 7 high schools with all of that fancy stuff. And though they've reduced their overall energy consumption by more than 20%, their bill has gone up 40% in the past 2 years. Okay. So and the utilities were surprised, honestly, to find this. When we did the project with SCE and EPRI, they were like, we walked them through. We did 12 hours of workshops with 30 facility managers. And we said, we've got 2 scenarios for you. We're going to introduce a new rate, just a time of use rate with a demand charge. We didn't even introduce like, hey, by the way, in 2027, all of your legacy NEM rates are going to go away. Like, we didn't add that complexity, that is reality now. We just said new TOU rate with a demand response. And it used to be there would be a new rate case every 5 years. Now we're going to do it every year. Hey, why not? Show us how you would solve that problem as a building operator. And we had every single one. Again, it was 12 hours worth of workshops in depth with 30 different facility managers. And they showed us in their building automation systems, in their Venstar thermostat portal. And honestly, the utility reps were horrified. They're like, what? Why do you have a 50% opt-out rate in your demand response and load flexibility programs? Because you are cycling compressors on HVAC in the middle of summer when seniors are taking their ACTs and they're sweating balls over here. Sorry, that is a technical term. And their parents call up your school and they're like, I don't know what you're doing. I don't care how much you think you're saving. You're going to stop now. And they said, you know, you're right. We have these huge opt-out rates. Traditional demand flex doesn't work. However, when we looked at the alternative, trying to give them the sophisticated controls, they were saying that they were spending 5 to 8 hours a week manually tuning schedules and set points on thousands of rooftop units to try to maintain comfort while reducing energy, these 2 pressures. And they were like, it's not doable. I've got 5 guys for the whole district. They were literally raking mulch and cleaning up vomit. I do not have time to babysit this. Like, it is insane. And so we went out and said, isn't there a way? This is one of those things where it's just like, you know that quote, the JFK quote, we don't do this because it's easy. We do it because it's hard. And there's that like meme that's like, we do this not because it's easy, but because we thought it would be easy. And that was me 4 years ago. So I was like, but surely, I mean, someone must have created a way to both keep people comfortable and save energy. Golly, Jimmy. Went out, secured about, after that EPRI contract, secured since then about $6 million in research and development funding through NSF, USDA, Department of Energy, Washington Department of Commerce, CEC, people very interested in sort of helping this segment figure this out, and realized exactly why it's so hard, because thermal modeling of buildings is tough. But we're there. We're at the cusp. So we looked at a solution that could maintain comfort, really focused primarily on HVAC. Could be installed in less than a day, primarily with sensors that already exist in the building, i.e. thermostats and other types of data like weather, a dynamic, we are participating in SCE and PG&E's flexible rate program. So we respond to a price that changes every hour with a 24-hour in advance forecast, thank you. It can be installed for less than $20,000. That's a critical threshold. If you're a public purchaser in the state of California, you can be a signatory to something called CUPCA. It means that anything that you can procure through your maintenance operations budget for under $50,000 can be purchased on a sole source procurement. You don't have to go out to bid, which is a pain in the ass for the vendors and a pain in the ass for the schools, it turns out, and as we mentioned before, already raking mulch, cleaning up. Research and development timeline. There are sort of two primary components of the technology. The hardware, let's think about first the business model. The business model is a lot like your Verizon, your phone. If you're a Verizon customer, Verizon doesn't make the iPhone. They sell you the iPhone so that you will buy their service, which is a monthly service that manages your data usage and provides, telecom. Similarly, this is the business model here. The service that we provide is energy management in response to a real-time or a flat rate or a time of use rate around HVAC while providing comfort in a hands-off way. That is the service. Sometimes, however, in order to be able to provide that, we may have to install hardware that we do not own or operate. So you won't hear me talk about the hardware really at all, because it enables our business model, but it's not super critical. Let's just put it this way. Most of these customers need to have a building automation system that uses BACnet over IP. Almost every California school district has that, or a wireless thermostat that has an API that we can talk to. I definitely have run into pneumatics, but it's not super expensive for these districts to upgrade. Okay, so there are three parts to the research that we did. The first one is model predictive control. Has anyone heard of model predictive control? Yeah. Kind of like the holy grail of buildings. It's been used in industrial automation for decades. It creates a model of a system, and it uses that model to make predictions and forecasts about that system's behavior such that it can be optimized. Model predictive control is the gold standard for building controls, saves 28% on average more than competing technologies. But it is basically, I say it's a holy grail for one important reason. Does anyone know what the Achilles heel of model predictive control in buildings might be? Yes! It's very expensive to create a building model because of the heterogeneity of buildings. Extremely expensive. So the average reference model, there are about 16 reference models from the Department of Energy for calculating an Energy Plus model of a building. And the DOE has been amazing at funding and creating tools like the DOE Asset Score, which allow us to baseline these buildings for regulation and other purposes. However, for optimal control, those are not accurate enough models. To create an accurate model of a K through 12 school, a primary school, for example, typically takes 433 parameters, some of which are measured, some of which are calculated, costs anywhere from $10,000 to $50,000 to create that model. That's just the model. Then you have to, actually, I'm going to go into these details in a minute. I'm like, okay, Tanya, come back here. So MPC, if we could do it, if we could do MPC and make it cost effective, that would be incredible. We were like, we want to be able to try to find a way to do this. How could we go to market and do MPC? And how can we do it in a way where we reduce the biggest cost, which is the energy modeling? So to cut to the headline, we were able to reduce 80% in energy modeler time and cost, and use, I would say now it's even less than this, less than 40% fewer hours to collect the data, with an overall reduction in cost at the end of our phase 2 SBIR from the DOE of 27 to 56%, depending on the size of the building. The second component, this was funded by NSF, is creating a model framework that's flexible enough to be picked up and put down on multiple types of buildings, despite their heterogeneity, and could still accurately learn and deploy the model. Now, this is not to say that the model framework that we chose will work on all buildings and all systems, but through our research, and I'll go into that in a minute, we were able to identify 2 primary types of building and HVAC topologies and geometries where this technology could work most of the time pretty well. So the machine learning then is used to generate the model used in model predictive control, and also the machine learning updates that model and does the actual control with the building. So these were the 2 sort of wings of the bird in terms of research in order to create that stack that we talked about before. Okay, on to the next slide. So this is, I already kind of talked about model predictive control, what it is and what it does. You have an input sequence, you have a building. It estimates the properties of the building in order to predict the thermal behavior of the building and to make good decisions based on that prediction. But, bada boom, bada bing, that is the Achilles heel at the bottom. That building model is the deal breaker. So next slide. If we look at the average primary school, 73,000 square feet in the United States, the BAS, their building automation system, is going to cost $150,000 to $250,000 installed. And then not even looking at how much it costs to do the model. Like again, that would be, let's say, $10,000 to $50,000. You're going to need to spend $50,000 to $130,000 to try to reconfigure the rules and the operating procedures of their BAS or their thermostats in order to do something. Workflows that would allow us to collect some of these sensitive parameters in ways that would be faster and cheaper. We created 7 alternative workflows, and we began testing those workflows against 133 K through 12 buildings in Oregon, Washington, and California. We collected all of their building blueprints, their mechanical electrical drawings, their thermostat manufacturer manuals, and a bunch of data about all of these, and said, how long does it take us to actually collect the parameters that we need? Am I over on time? Okay. All right, next up. And yeah, it felt a little bit like boiling the ocean. But eventually we were able to see which parameters not only had the biggest impact, but which ones were the most time-consuming and costly to collect. And we began optimizing those workflows by automating pieces of those workflows until, spoiler alert, oh, sorry, this was a little bit of background. We were able to reduce the number of parameters needed to generate an accurate model with only 6 days of sensor data from 400 and whatever I said before, 430 parameters to 57. And now we're, I think, closer to 30 or 40 parameters, many of which can be collected through a thermostat, some of which are collected from building drawings or what do you call it, Google Maps. So this is just an analysis of the types of sites that we looked at. These are the building, sort of generic building types. Next up. We also had some multifamily in there and some commercial. These are the energy source types. So you can see most were primarily gas and electric, gas, heat, electric cooling. But there are an increasing number of all electric HVAC fuel sources, okay? One thing that we saw is that there is about a third are older than 20 years. They're beyond end of life. Again, saying what I was saying before, that it's difficult for them to find capital projects to replace these, and they tend to replace these units as they fail. So we are seeing more and more electric units come online as those drop out. Okay. Ruthless efficiency, this is just saying, you know, we're looking at 2 very different types of buildings. This is Newport Mesa Unified School District, Sonora Elementary. It's this cute little campus right here. It's all just a bunch of freestanding buildings, basically. And then here you have Century High School. So you're seeing a sort of, we looked at a wide range of buildings that we put the data through. And then as people were going through that job task analysis, you can see this is a building engineer's time logging. We would log their screen activity every 10 minutes. To see, in fact, how much effort they were putting into, how much effort they had to put in, and then we would multiply that times their wage for each of the task flows. Okay. So let's just keep going. Here are some of the results once we implemented this. So then after that, after we developed the prototype, we launched it in the field with about 23 different campuses, hundreds of buildings. This is from the first set of tests in Washington and California. This is Washington. They use a flat rate tariff. And so we ran, using these predictions, we put it into the ML model. Right now, it only works with HVAC topologies where there is a single space, a single unit, and a single thermostat. We are developing a new algorithm for VAV and air handler units. But these are some of the results, and these were published in the Journal of Energy and Buildings in 2024, I believe. The yellow is the baseline energy consumption, and the blue is the consumption with the, I call it the robot, the virtual engineer. So you can see there's a pretty significant decrease during operating hours. This is morning warm-up at that site. And you can see it's not needed. You know, a lot of times those rules-based settings are just they're trying to like superheat. This is typical rules-based set point-based control. So this is the cooling set point. You know, somewhere before this, your system hits that temperature threshold and begins to cool. Your temperature will drop, you know, potentially underneath your ideal set point threshold. And what will happen is the compressor will come on. So what you're seeing here is a single compressor for each of the classrooms. When it's up, it's cooling. When it's down, it is not. And the blue is the aggregation of all of those. So what you're seeing right here is that you probably have, you know, I don't know, we have 21. You probably got like 17 compressors running at the same time for 2 hours. I'm here to tell you that's going to set their demand charge for the month. That's typically how it happens. It's just this lack of coordination between all these RTUs means they're all running at the same time. So take a look. What we see, too, in these buildings, these commercial buildings, is that when we look at the energy meter, and we're 1 minute done? Yeah. OK. I'll try to wrap it up really quickly. When we look at the energy meter, this corresponds almost exactly with the load shape of the buildings. And that's in the published study that we have. So, you know, you see these rules-based control, they just try to turn everything off. They put the set points at like 95 and 55 at 4 p.m. And what happens is people just override it and you get another peak that becomes very costly later in the day due to comfort. So now let's look at it with do you notice the difference in that load curve and the difference in the temperatures? The temperatures are much tighter. They fluctuate far less in the actual rooms controlled, and at the same time, you're engaging mechanical cooling less because you're allowing the rooms to coordinate all of the units and to coast. It's looking forward and saying, that room is gonna maintain a temperature of 70 for another 10 minutes. I do not need to heat that or cool that. It's not basing it on, oh, the temperature has now drifted to here, I'm gonna turn on the compressor. It says, I actually know what's going to happen in that room and can make an intelligent decision. So that's some of the work that we did on MPC. I don't know what I have. I'm happy to talk to people at lunch about the many lessons that we continue to learn. A lot of them are just like practical stuff, like what happens when you let a bunch of PhDs build your product. Please, let's talk later today, and I would be happy to share. Just let me cry. Thank you.